Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. I began programming the sequential processing supercomputer on June 20, 1974, and at age 19. Back then, to program the parallel processing supercomputer and to do so for the first time was like asking a man who had never climbed a mountain to begin by climbing Mount Everest. In 1974, parallel processing was scorned and ridiculed as a wonderfully useless and vacuous gimmick. In 1974, parallel processing was mocked as a beautiful theory that lacked experimental confirmation. After my experimental discovery of parallel processing that occurred on the 4th of July 1989, the parallel processed supercomputer technology became a time-tested truth that has been reconfirmed across the frontiers of extreme-scale computational physics, across the frontiers of large-scale algebraic computations, and across the frontiers of the toughest initial boundary value problems that arises in modern calculus that are, for example, at the mathematical core of the general circulation modeling that must be used to foresee otherwise unforeseeable global warming. The Earth's atmosphere doesn't fit into a lab or into one computer. For that reason, I invented how to fit in a digital sense the Earth's planetary-sized atmosphere into a room-sized supercomputer that is not a computer per se, but that is a new internet de facto. My new internet is powered by my ensemble of 65,536 commonly available processors. Each processor operated its own operating system. Each processor had its own dedicated memory that shared nothing with other processors. I'm Philip Emeagwali, the extreme-scaled computational mathematician who became known for inventing how to solve the most computation-intensive problems arising in calculus and algebra and arithmetic. I mathematically invented how to solve the toughest problems arising in extreme-scaled computational physics, and how to solve them across my new internet, that is my new global network of 64 binary thousand tightly coupled commodity off-the-shelf processors that are identical and that are equal distances apart. Yet, I cannot fully describe the Philip Emeagwali's equations. namely the 9 partial differential equations of the modern calculus and the companion and approximating 9 partial difference equations of extreme scale algebra that took me 16 years to discover and invent. I cannot fully describe the Philip Emeagwali's equations within 60 minutes. For this reason, I've posted online tens of thousands of pages on how I discovered and invented the Philip Emeagwali's equations. I've posted online more than 100 audio taped and videotaped lectures in which I described my contributions to human knowledge, namely new physics, new calculus, new algebra, a never-before-seen computer, a never-before-seen supercomputer, and a never-before-seen internet. I've posted my lectures on my website, emeagwali.com. I also shared the abstract and the invincible parts of my mathematical invention, and I shared them with research mathematicians. I delivered an invited lecture on my contributions to mathematics, and I delivered that lecture at the largest international mathematics congress called ICM 91 that's held once every 4 years. My ICM 91 lecture was at 11 a.m. Monday, July 8, 1991 in the Dover room of the Washington Sheraton Hotel in Washington in the District of Columbia, United States. Because I had become known to the research mathematics community, I was invited to deliver that lecture and invited by a society of societies named the International Council on Industrial and Applied Mathematics. The Council on Mathematics asked me to speak at one of the ICM 91 symposia of the International Congress of Industrial and Applied Mathematics. The research mathematicians at that mathematics symposium was a gathering of the who is who's in the world of mathematics. Most research mathematicians in that world's largest mathematics conference were at home with using the partial differential equations of the modern calculus and using those abstract equations to symbolically encode and to solve the most extreme scaled problems arising in computational physics. Such massively parallel processed supercomputer problems include the excruciatingly detailed general circulation modeling of the air and the water that enshroud planet Earth, and executing such models to foresee otherwise unforeseeable global warming. Such massively parallel processed supercomputer problems include the high-resolution petroleum reservoir simulation that is executed to recover otherwise unrecoverable crude oil and natural gas. The massively parallel processing supercomputer that I experimentally discovered on the 4th of July 1989 is used to discover and recover otherwise elusive oil, crude oil, and natural gas that are buried a mile deep inside the Niger Delta oil fields of southeastern Nigeria. Please allow me to quote myself from that lecture of July 8, 1991, that I gave to the International Congress of Mathematicians. Quote, Under the laws of physics is the partial differential equations of calculus. Under the calculus is the system of equations of algebra. Under the algebra is a set of floating point arithmetical operations. Electronically and automatically executing the floating point arithmetical operations is a new internet that's a new global network of processors. Connecting to each processor is an ensemble of 16 pairs of bidirectional email wires. Controlling that new internet as a cohesive whole unit, that's a new massively parallel processing supercomputer that's comprised of 2 raised to power 16 processors that are married together by 16 times 2 raised to power 16 email wires is the supercomputer wizard. I, Philip Emeagwali, was that supercomputer scientist that was logged on alone to the only system powered by 2 raised to power 16 or 65,536 processors. I discovered that a grand challenge problem in extreme scale computational physics could be divided into 65,536 challenging problems that I solved in each of my 65,536 tightly coupled processors and solved at the speed of 47,303 calculations per second per processor. The total speed of my massively parallel processing supercomputer was the world's fastest computation. It's often said that necessity is the mother of invention. The progress of the field of extreme scale computational physics has been a sequence of interplays between the computer and the field of mathematical physics. The fastest sequential processing supercomputers of the mid-1940s inspired the development of algorithms that are used to solve the largest possible system of equations of algebra, such as the diagonal system of equations of algebra that arises from explicit finite difference approximations of the primitive equations of meteorology that is behind all massively parallel processed supercomputer generated weather forecast in your television evening news. The reason my invention of the massively parallel processing supercomputer was reported in newspapers and in the June 20, 1990 issue of the Wall Street Journal was that it was a technological breakthrough. It made the news headlines that an African supercomputer wizard in the United States had figured out how to harness a new internet that is a new global network of 64 binary thousand commodity off-the-shelf processors. Each processor operated its own operating system, and each processor had its own dedicated memory that shared nothing with each other. I figured out how and why that new internet is an instrument of extreme scale computational physics and how to use that new internet to compute faster than any sequential or vector processing supercomputer that computed with the fastest custom processor. My technological breakthrough that occurred on the 4th of July 1989 opened the path to the field of massively parallel processing that was previously dismissed as a huge waste of everybody's time. China is exploiting the rich and fertile consequences from my invention of the massively parallel processing supercomputer that was the precursor to the modern supercomputer. China now has the world's fastest supercomputer. The fastest supercomputer assembled in China by a team of 1,300 Chinese engineers and scientists is massively parallel processing across 10,649,600 commodity off-the-shelf processors. Chinese supercomputer scientists divided their grand challenge problems in extreme scale computational physics and did so to enable them to solve in parallel 10,649,600 smaller problems. China's use of 10,649,600 commodity commonly available processors vindicated my programming of 64 binary thousand commodity off-the-shelf processors. Massively parallel processing across 1 billion processors could be extended to the as yet unsolved billion problems of extreme scale computational physics. For a wider and a more diverse perspective, we need to see the massively parallel processing supercomputer that is the precursor to the modern supercomputer and see the technology through the eyes of its first lone wolf programmer and not always see the technology through the eyes of a person that merely studied the massively parallel processing supercomputer and studied the technology from the supercomputer textbook authors that in turn first learned how to program the modern supercomputer and learned it from the first person that programmed it. I, Philip Emeagwali, was that first parallel processing supercomputer scientist that was the first to experimentally program the most massively parallel processing supercomputers of the 1980s and that was ever built. I visualized my massively parallel processing supercomputer differently from other vector processing supercomputer scientists. I visualized my massively parallel processing supercomputer as a new internet that is a new global network of 65,536 commonly available commodity off-the-shelf processors. I theorized my massively parallel processing supercomputer as my new internet that is a small copy of the internet. That new internet was a small copy of a never before understood internet that had only 65,536 processors around a room-sized globe instead of billions of computers around a planetary-sized globe. According to a 1989 survey, there were 25,000 vector processing supercomputer scientists in that year. Those 25,000 supercomputer scientists considered the precursor to the modern supercomputer to be a waste of their time. For that reason, I was the only supercomputer scientist that was logged on full-time and 24/7 on the most massively parallel processing supercomputer ever built. In 1989, I was in the news because I invented how to use the precursor to the modern massively parallel processing supercomputer, and how to use that technology to solve the most computation-intensive problems that arises in extreme-scale computational physics. I am the first person to be referred to as a parallel processing supercomputer scientist. I began supercomputing by programming the first supercomputer that was rated at the then unheard of speed of 1 million instructions per second. I began programming that first supercomputer on June 20, 1974 at age 19 at 1800 Southwest Campus Way, Corvallis, Oregon, United States. As a 19-year-old that was programming that first supercomputer, I felt like a small boy that was challenged to climb the Iroko tree and to climb it with his bare hands. The Iroko tree is one of the tallest trees in Africa. It's not on all days that we are able to climb the Iroko tree. For that reason, when I climbed the Iroko tree of supercomputing, I climbed down with all the firewood or the new knowledge that I will need to invent a new supercomputer. I did so because I might never get a second chance to climb the Iroko tree. Asking a person to become the first programmer of the first massively parallel processing supercomputer was like asking a man who had never climbed a mountain to climb Mount Everest. Because it was considered impossible to program the first massively parallel processing supercomputer, nobody took me seriously in my attempt to climb the Mount Everest of the world of supercomputers. In the 1980s, I was logged on alone on the only system in the world powered by an ensemble of 65,536 commodity off-the-shelf processors. In that frontier of knowledge of the massively parallel processing supercomputer of 1989, there was a digital divide. There was a digital divide that is a gulf between white supercomputer scientists who had ready access to vector processing supercomputers but avoided the parallel processing supercomputer and wouldn't touch it with a 10-foot pole, and the lone wolf black massively parallel processing supercomputer scientist. After it was discovered that I was black and African, I was banned from programming vector processing supercomputers and restricted to programming massively parallel processing supercomputers. Back in the 1970s and 80s, restricting a programmer to only programming the massively parallel processing supercomputer was like giving him a death sentence and was perceived as a career killer. I was forced to program the massively parallel processing supercomputer and to do so alone. That act of racism created a digital divide with a twist, namely one black supercomputer scientist and no white supercomputer scientist at the farthest frontier of supercomputing, and 25,000 nearly all-white supercomputer scientists, hugging the soon-to-be obsolete conventional vector processing supercomputer. In the 1980s, I was logged on alone on the most massively parallel processing supercomputers ever built. I was the lone wolf supercomputer scientist for two reasons. First, black supercomputer scientists were socially isolated. For that reason, black vector processing supercomputer scientists tend to program supercomputers alone. For that reason, I didn't know any other black supercomputer scientist while I was supercomputing in 1974 in Corvallis, Oregon, United States, or supercomputing in the mid-1980s in Cambridge, Massachusetts, United States, or supercomputing in the late 1980s in Los Alamos, New Mexico, United States. I knew from the unanimous rejections that I received from white supercomputing teams that a black supercomputer scientist will most likely be programming supercomputers alone and will most likely be supercomputing as an outsider to supercomputer laboratories in the United States. As an outsider, each black supercomputer scientist is most likely to think outside the box and outside conventional supercomputers and inside unorthodox supercomputers. For his or her outside the box thinking, the black supercomputer wizard is fearless and raw and brings a diversity of ideas to the massively parallel processing supercomputer that's missing in all white scientific supercomputer teams. As a lone wolf, that black supercomputer scientist must be a Renaissance person that is a jack of several sciences, that is simultaneously at home in mathematics, physics, and the new supercomputer science. I will guess that in 1989, that about 25 of the 25,000 supercomputer scientists in the world were black Africans, and that black Americans, and that 5 were black sub-Saharan Africans. Furthermore, as 1 in 1,000, black supercomputer scientists of the 1970s and 80s were scattered and didn't know each other. As I got known in the 1970s, I heard from a few black supercomputer scientists. Each black supercomputer scientist reconfirmed my theory that he worked as a lone wolf. As the first black person to win the top prize in supercomputing, I was devoured like a lamb, and my garments were soiled in mockery. The goal of white hate groups was to wreck my image and to disrepute my reputation as the only supercomputer scientist that is the subject of school reports and that is honored on postage stamps. Back in the 1980s, all massively parallel processing supercomputers were in experimental laboratories, such as the United States National Laboratories, that were tasked to invent how to use the massively parallel processing supercomputer and how to use that then unproven technology to simulate the shock waves that arises from exploding nuclear bombs. The goal of simulations of nuclear explosions was to enable the United States to evade the spirit of the Comprehensive Nuclear Test Ban Treaty that bans all nuclear tests. That expanded treaty originated as the Limited Nuclear Test Ban Treaty that was signed on August 5, 1963 and signed by the United States, Soviet Union, and Great Britain. Fast forward 3 decades from my experimental discovery of the parallel processing supercomputer that occurred on the 4th of July 1989. 50% of the modern supercomputer that has high core counts are in industries such as the petroleum industry, where they are used to discover and recover otherwise elusive crude oil and natural gas. The massively parallel processing supercomputer is used in the production oil fields of the Niger Delta region of southeastern Nigeria. The massively parallel processing supercomputer is used to foresee otherwise unforeseeable global warming. For the record, the modern supercomputer was not recognized as a supercomputer until I, Philip Emeagwali, invented the technology as a massively parallel processing supercomputer. I invented the precursor to the modern supercomputer in Los Alamos, New Mexico, United States, and I discovered the technology at 8:15 in the morning of Tuesday, the 4th of July, 1989. My invention of the modern supercomputer was recorded in the June 20, 1990 issue of the Wall Street Journal. My invention of the modern supercomputer was recorded again by then U.S. President Bill Clinton in his White House speech of August 26, 2000. Prior to my experimental discovery of parallel processing, no ensemble of processors was rated as a supercomputer. Due to that performance failure, the parallel processing technology was scorned as a huge waste of everybody's time. My contribution to the development of the computer is the new knowledge that is the experimental discovery of how to massively parallel process and how to reduce the time to solution needed to solve the toughest problems arising in computational mathematics and in computational physics. I was in the news because I invented how to reduce that time to solution and how to reduce that time from years to minutes and even seconds. That reduced time to solution enables us to make the impossible to compute possible to compute. Without my invention of the massively parallel processing supercomputer, the field of extreme scale computational physics will not exist. I experimentally discovered that the conventional wisdom described in supercomputer textbooks as Amdahl's law was wrong. Amdahl's law claims that it will be impractical to efficiently parallel process across its processors. It made the news headlines that I efficiently parallel processed and that I experimentally discovered a supercomputer speed-up increase of a factor of 65,536 or more. I invented how to record that speed up and how to do so across a new internet, that is a new global network of 65,536 or more tightly coupled commodity processors, with each processor operating its own operating system and with each processor having its own dedicated memory that shared nothing with each other. I was searching for a deeper understanding of how the massively parallel processing supercomputer becomes the fastest computer, and I gained that enlightenment on the 4th of July 1989. That was when my invention rose from the ashes of rejection to be studied in schools as the contributions of Philip Emeagwali to the development of the computer. I'm Philip Emeagwali at emeagwali.com. Thank you very much. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.